IITs में पढ़ने का या PSUs में जॉब करने का? तैयार हो जाइए एक स्मार्टर अप्रोच के साथ गेट 2022 क्रैक करने के लिए। प्रिपेयर करें स्मार्टली गेट 2022 के लिए गेट अकेडमी के साथ। ज्वाइन करें गेट अकेडमीज स्मार्ट कोर्स और पढ़े इंडिया के टॉप फैकल्टीज के साथ एक स्मार्ट तरीके से। तो देर किस बात की, अपना स्मार्ट कोर्स बुक करें आज ही और साथ में पाएं फ्री ऑनलाइन टेस्ट सीरीज और वर्कबुक PDFs। ऑफर वैलिड होंगे 4 सितंबर 2021 तक। एडमिशंस क्लोज होंगे 4 सितंबर 2021 को। तो मौका है यही, ग्रैब करो ऑफर अभी और क्रैक करो गेट 2022 सभी। विजिट करें gateacademy.co.in पर। अपने सपनों को दें एक नई उड़ान गेट अकेडमी के साथ। क्या आपका सपना है टॉप IITs NITs में पढ़ने का या PSUs में जॉब करने का? तैयार हो जाइए एक स्मार्टर अप्रोच के साथ गेट 2022 क्रैक करने के लिए। प्रिपेयर करें स्मार्टली गेट 2022।
Hello my dear lovely students. So in the back you are seeing this, and also I'm not coming live, I'm coming to you on a premiere mode. Why? There's a reason for that. Meanwhile, tomorrow you have your marathon. There's no denial to that. And tomorrow we are finishing up with this thermodynamics, our subject. But at the same time, today I have some important piece of work at my home which I cannot, ignore. It's related to health of my family member. So I have to go and, do the due processes. So that's why I am not available to you on the live mode. I'm really sorry for that. But tomorrow we'll be live for sure at 2 p.m. And let me tell you this. We'll be doing today the questions, the problems of entropy, availability, and also if time permits, we'll be doing the solution, right? We'll be doing, not the solution so we are doing. But apart from that, we'll be beginning with the thermodynamic relations, which is an important integral part of a course or your syllabus. So that is something which we need to take care of. We'll be dealing with Maxwell equations and short trick to remember them. So this is a very important lecture. Stay till the end and you will enjoy the benefits, right? So today I won't share it to everyone, session share karo, this then that. I won't be doing that, but yeah, it's my humble request that you please share this session amongst everybody. Now, this is question number 4.4 because we have done already the previous questions. And in 4.3, there's a question that according to second law of thermodynamics, for a process to be feasible, which of the following should be true? So the change in entropy for feasible process must be less than or equal to 0. Means for a universe, entropy changes delta S. See, delta S universe is either greater than or equal to 0. Means positive or 0. If it is 0, it is reversible. If it is positive, it is irreversible. Yes or no? Yes or no? Right? But for a system, if the process is reversible, it can be less than 0 for a process, reversible process only. But it is given feasible. In feasible process, for a change in entropy for a system is always either positive or 0, never negative. That's why 4.3 option A, because of the word feasible. Now, these properties are given. It's nitrogen gas. It is undergoing an isothermal expansion from 1 meter cube to 2 meter cube. Initial pressure and temperatures, which final are, and also T0 surroundings temperature is this. Now, since it is isothermal expansion, work is asked in 4.4 and work is calculated simply. P1 V1 ln V2 by V1. We have derived this formula, by the way. Okay. Now coming on to this question 4.5. In this, change in entropy of the universe has been asked. So if you see, it is an isothermal process. During an isothermal process, the change in entropy is what? 0. Yes or no? Thus the change in entropy, and that is equal to what? Change in internal energy, sorry, and that is equal to what? 0. Right? Change in internal energy is 0 for an ideal gas. Now if you apply this, del Q equals del W. Since del W is coming positive, del Q will be positive too. If del W is coming positive, del Q will be positive too, right? Heat supplied to the system. Okay. Now delta S surroundings. Delta S surroundings is like del Q surroundings upon surroundings temperature. So what is this del Q surroundings? How do we define this del Q surroundings? See, for system it is supply. Positive means for system it is supply, and for surroundings it will be rejection. See, if system is getting heat, it is getting from where? From the surroundings. If system is getting heat, receiving heat, from where is it getting? It's getting from the surroundings. So system is receiving heat from the surroundings. Negative sign is there. Negative sign is there and negative sign will be there. Right? And it is rejection. Why? Because surroundings is rejecting it to the system. So for surroundings it is negative, hence negative sign. So equation number 1. I'm not doing the calculations. I'll simply tell you the steps. Calculations you have to do. At least do something on your part. Right? Anyways, so in order to calculate delta S system, certain properties are given, which is nitrogen. Nitrogen gas is the system. So you need to apply TDS equations according to the properties. And since du is 0, just simply apply this equation. No need to go for that other one. Although you can find it out, but there's no need altogether. Anyways, so now let's move on to this one. So it is ds equals to P by T dV. T will go that side, P by T dV. Now ds of nitrogen is mR dV by V, right? So m into R will be PV by T. So I have done this PV by T1. Integral volume is actually changing from 1 meter cube to 2 meter cube. It's not just the states I'm saying volume is changing from 1 meter cube to 2 meter cube, dV by V. Simple as that. So it will be ln2 log 2, right? And P1 V1 log 2. Doesn't it look like this? Upon temperature, T1 is same as that of surroundings. So I think change in entropy will be 0 for universe. You can solve them. Put them and solve them. You'll get the same result. Okay, everybody? Yes or no? So please take the screenshot. Then we'll move forward. Please take the screenshot. Then we'll move forward. Please do that. Okay. Now, next let us go with question number 4.6. 4.6. Let's see what does it say. 1 kilogram of water at room temperature is brought into contact with a high temperature thermal energy reservoir. Entropy change. See, water is at room temperature. There's some water. It is at room temperature T0, right? And this is brought into contact with a high temperature source, right? High temperature. That means heat is being transferred. And there is a finite temperature difference, isn't there? Yes or no? There is a finite temperature difference. So if there is a finite temperature difference, yesterday only I told you that the disturbances in equilibria due to finite reasons is always what? Is always what? Leading to irreversible. So the process is an irreversible process. Now if the process is an irreversible process, then what do we need to do? If the process is an irreversible process, that means delta S universe will be greater than 0. Okay. So universe is greater than 0, always positive. Option number D. Alright. That's your question number 4.6 for you. Now we have 4.7. It is the same. We have done this problem just in theoretical terms. See, that's why I tell you why theory is important. Just by simply seeing this question, you might be able to identify it. For example, there are a few parts in this, right? There are a few parts like number 1, number 2. Okay. Number 1, and then you have number 2. So what do you have here? 1200 Kelvin loses. Oh, sorry. Yeah. 1200 Kelvin directly loses 2500 kilojoule, 2500 kilojoule to what? 800 Kelvin. And in second case, 800 Kelvin is there, and this reservoir is losing to 500 Kelvin. How much? 2000 kilojoule. Is it clear? Is it clear? Okay. Now let's get to the conclusion part, that the delta S universe, we have already although seen the formula, haven't we? We have seen it. But if you want, I'll repeat it. Don't worry. Suppose this is my system. It is leaving the system. So minus del Q by T minus 2500 over 1200 plus surroundings. It is, if this is system, that is surroundings, going in 2500 over 800. About here, what do we have here? Leaving, let's say this is the system, 2000 minus 2000 because it is leaving by 800 plus 2000 by 500. Okay, let's deal with this here. I think it is 25. I'm just cancelling it out, right? Yeah, 2500. And I'm not saying 2500. 1 by 8 minus 1 over 12, right? And over here we have 20. This is 20. 1 over 5 minus 1 over 8, isn't it? Now how to solve this? 25, and this is 12 minus 8 over 12 times 8, correct? And this is how much? 20. 8 minus 5 over 8 times 5. Now you can solve them. And whosoever, whichever entropy is coming higher, whichever value is coming higher, that is irreversible. Right? Process 1 is more irreversible, less irreversible. That you can do judging on the value of delta S irreversible. Right? Please take the screenshot, everyone. Please take the screenshot. Yeah, so I think you must have taken the screenshot. If not, if still, then you can take. Okay, actually I recorded it, and in that recording what happened, there was no sound, so I have to re-record it. Anyways, no worries, no problem. Let's deal with it. Now, since I have written everything, so I'm not going to rub it off. Okay, I'm going to explain it to you what is happening. Now 4.8 and 4.9, they are common data questions, right? They belong to common data category, and this question has already been taken in the class. Means this type of question, it's, you remember, air is flowing from station 1 to station 2, right? Air is flowing from station 1 to station 2 and this and that. So that question we have already done. That type of question we have already done. And it is similar to that. Even if still you are facing a problem, let me tell you, it belongs to PKNAG. Example 7.6 in the old book or 7.9 in the new book, new edition. Depending on where it is given. Okay. It has been asked in both civil services as well as engineering services exam. And let's move on to 4.10, next question. So in that question, isothermal process was given, and over here temperature is constant, right? Temperature is constant. And if we go with the first law of thermodynamics, we have del Q equals du plus del W. right? Del Q equals du plus del W. That is there. Now what happens is, isothermal ideal gas du will be 0. Del Q will be equal to del W, and del W will be delta S gas will be, since it is isothermal, del Q by T only, means del W by T. P1 V1 over ln P1 by P2, P1 by P2 upon T1. Since it is given in terms of pressure, hence it can be done like this. Now I just cancel T1, I get this, and this, my dear students, is my result. Option C would have been correct if it would have asked overall, but it is saying only for gas, so only this is correct. 4.11, we have this block, heat is supplied to it. From this wall heat is supplied, from that wall heat is being rejected. Now delta S universe will be wall 1 plus wall 2. This is leaving this wall, that is why minus, because it is leaving, upon temperature. This is supplied, hence 100 by 300. Solution. You do the solution part. I'm just giving you the steps. Solution you will do. Okay? Please take the screenshot. Okay, now I think you might have done this. Let's move on to the next question. Set of questions. 4.13, that's an important question. Why? Because it is different type of altogether, and mind it, this kind of questions we have done already. How? See, it's given that this is a block of finite capacity. This is the same block of finite capacity. Now the only difference being, although they are at same temperatures, initial temperatures are same, I am applying a cyclic refrigerator in between, so that this refrigerator is taking out heat from here, low temperature, and supplying to the high temperature. So that is happening. Meanwhile, it is taking in some work. Now it is given that you please see in your books, question is there. Now please pay attention that this is a reversible refrigerator. If the refrigerator is reversible, then the delta S universe will be what? 0. Delta S universe will be 0. Means system plus surroundings is 0. And let us say this is your system. For system we can say 0 because it is cyclic. Am I right? Because it is cyclic, delta S system will be what? 0. And now for surroundings we have block L and block M. Both of them we have. So that means, since these are solid blocks, dV will be 0, mc dt by t, integral, we have this. Now add them up and put them to 0. See, 5 into 0.4 is 2. 5 into 0.4 is 2. ln this equal to 0, you will find out TMF. It's very simple. Equal to that, you will find out the value for TMF. Okay? Please take the screenshot. Is it done? Okay. Now, let's move on to the next question. 4.14. Now, in this question, what's there is, it is given that some properties are there, right? Some properties have been given. Now, while giving these properties, temperature was given as constant. You can check for yourself. Temperature is given. Let me tell you, I have the book in front of me. The values of temperature are 20 degrees Celsius in both the states. It is given 20 and 0.9. Yeah, 20, 0.9 degrees Celsius, 20 0.6 meter cube. So this is given. If that is given, you can calculate change it through change in volume. You can find out ds because dt is 0. Another question is similar to this, but only pressure is given. In place of volume, pressure is given. So you'll use this equation instead of that one. Same question. 4.17, what about that? That is similar to this one, but the only difference being that now temperature and pressure both are given different. So dH won't be 0 like in this case. You can do this. Next 4.18, let me tell you what that question is. It is based on theory. I told you I was doing this and it was recorded without voice. So that was another issue. Anyways, 4.18. Yeah. So it has been asked, how do you find out delta S of an ideal gas? Delta S for an ideal gas is CV ln T2 by T1 minus R ln P2 by P1. That's it. Yes or no? CV ln, oh, in option A, it is given CPA. It's not A actually. Let's see. Delta S CV ln T2 by T1 plus R ln, plus R ln V2 by V1. That will be correct one. And delta S will be, we have derived this already based on theory only, ln T2 by T1 minus R ln P2 by P1. So I think option number A is correct. Yeah, this is option number A. Option number A was correct. Understood? Rest of them are wrong. All the three are wrong. Now 4.19, that is similar to again these questions. Changes in temperature and pressure and everything is to be calculated. 4.21 is based on thermodynamic relations and this is 4.22. What about 4.22? Please check. In this question there is some intersection of the curves, right? And now over there the ratio is asked, dt by ds. So slope of constant pressure is this, slope of constant, you take the ratio, it will be CV by Cp. We have done this already, right? And then 4.23, that is similar to, please read the question. That question of yours is simply similar to the other parts. We have done that. Okay. So now we are going to start with thermodynamic. Entropy is done. Let's deal with another chapter, availability and irreversibility. That's yet another chapter, chapter number 5. Let's deal with chapter number 5. What does it say and how does it tell you? 5.1. Question 5.1. What does it say? It's a conventional problem. Earlier GATE used to be a conventional paper as well. 5 marks questions were asked. So this is one of them. Air expands steadily through a turbine from 6 bar 800 Kelvin, 1 bar 520 Kelvin. During expansion, heat transfer from air to the surroundings, means rejection is 10 kilojoule per kg. Neglect the changes, calculate irreversibility. How do you calculate irreversibility? Irreversibility is T naught into delta S universe. Yes or no? Right? So delta S universe, what about it? Won't that be delta S system plus delta S surroundings? Won't it be like this? So what about delta S system? How do we calculate delta S system? In order to calculate delta S system, let us deal with this. Some properties are given, right? So in order to do those properties, check out with those properties, you have TDS equations. TDS equals to DH minus VDP you will do. Why? Because changes in temperature and pressure are given. That is why. So DS equals to DH mCp dt over T, V by T dP, means mCp ln T2 by T1 minus mR ln. This we have done already. This derivation yaar, we have done, no? This will be delta S. So delta S system we have. Okay. pressure, temperature, but volume is not given, so let's take it unit mass, and also per kg it is asking. So in case of unit mass, it will be mass taken out or kept as constant, and MCP, it is not MR, my mistake, it is MCP. So it is going to be 1.005, values are given, 1 is given, not 1.005, 1 is given only, 1 ln 520/800 minus 0.287, or something else is given, I guess, 0.3, not 0.287, 0.3 ln 1/6. That will be delta S system. You will calculate, definitely, I know. Now delta S surroundings. See, for surroundings it is supply, because it is rejected by the system. So it is 10 kilojoule per kg, 300 kilojoule per kg Kelvin. Now add them simply. ln 52/80, 520/800 minus 0.3 ln 1/6 plus 10/300. Whatever be the answer, calculate it. That is your delta S universe. And irreversibility will be simply multiply T naught. T naught is how much? 300, I guess. Yep, 300 times delta S universe, whatever is coming here. If you do that, the product, that will be your answer. Okay, that will be your answer. Next problem, 5.2. A heat reservoir at 900 Kelvin is brought into contact with ambient at 300 Kelvin for a short time. During this period, 9000 kilojoule of heat is lost by the heat reservoir. The total loss in availability due to this process will be. See, what is given? It is asking that there is a reservoir. Okay, there is a simply reservoir. Let me do this. There is a reservoir which is at 900 Kelvin. And what does it do? It is simply giving off to 300 Kelvin. Now irreversibility what? Irreversibility will be loss in availability. Yes or no? T naught delta S universe, right? So how much is heat? Heat is there, 9000 kilojoule. That will be what? T naught is 300. At 300 it is available. Delta S will be, it is coming from 900 minus 9000 over 900. It is going to 9000 over 300. Right? You'll find the answer out. Okay? That's how your irreversibility will be calculated. Please do it. Okay, is it done? So I'm just telling you the steps. You people do the solution part, because I don't have Kelsey with me right now. Now you have 5.3. 5.3. Simple. Availability of a system at any given state is availability, maximum work obtainable, maximum useful work obtainable, maximum useful work. I've already told you that availability is nothing but maximum useful work of the system, right? That's how you treat availability with as. Okay, next move on to 5.4. Let's deal with 5.4. So what does 5.4 tell you? Yeah, considering the relationship TDS du plus PdV, which of the following is correct? It is applicable only for reversible. It is for irreversible. It is valid for ideal gas. It is equivalent to first law for a reversible. Yes. See, TDS equals to du plus PdV. It is derived from first law for a closed system. Del Q du plus del W. That is it. Now for a reversible, del q can be written as TdS, du, it can be written as PdV, right? Simple. So it is that, because it is saying in option B that TdS is greater than du plus PdV in case of irreversible. Is it true? No, it is totally wrong, right? Because for irreversible, reversible, it is valid, but it becomes first law if the process is reversible. Simple. It is equivalent to that. Next, question number 5.5. See, what did I tell you, earlier, that the availability concept is just an application of entropy. It is just an application of entropy. Whatever you study in entropy, that you apply here, because delta S universe is to be calculated, and that is very important. Okay, now see, a steel billet of 2000 kg mass is to be cooled from 1250 Kelvin to 450 Kelvin. The heat released during this process is to be used as a source of energy. The ambient temperature is 303 Kelvin. Specific heat is this much. Available energy will be. So, how do we calculate the available energy? See what has been given. So the values which have been given already are, see, mass is there, that is 200 or 2000 kg, right? Temperature T1 1250 Kelvin, 1250 Kelvin to 450 Kelvin we are going. Am I right? 1250 to 450. And the ambient temperature T0 is how much? 303 Kelvin, and specific heat is 0.5 kilojoule per kg Kelvin. All right. Now, how do you calculate available energy? Will be heat supplied minus T0 into delta S. Yes or no? Heat supplied minus T0 into delta S. Say yes or no. See, since it is solid, incompressible, means TdS, I can use TdS du plus PdV. dV will be 0, TdS will be du, or I should say ds will be mCV dt by t, or mc dt by t, because Cp Cv are equal in case of a solid. Am I right? That is our TdS. Now moving on to the next part. So let's find out delta S. Delta S is very easy. Now you can do that. Delta S is mc ln T2 over T1. That is 2000, 0.5 ln. It is going to 450 from 1250. Am I right? It is going from like this. Understood? And simple. So available energy would be heat released. What? Heat released. How much is heat released? That will be mc delta t. M is 2000, 0.5, delta t is 1250 minus 450 minus T0, surroundings is at 300, into this 2000, 0.5 ln. This will be 1250 upon 450. Do you know why? Let me tell you. The reason being, because in this we have already considered minus sign. That is why. Because we have already considered minus sign. Negative sign has been already considered. That is why we are doing this. Okay. Now please take the screenshot. We'll move forward. Please take the screenshot, my dear students. Then we'll move forward. Please do that. Okay. Now shall we? Okay. Fantastic. Okay. So next is 5.6. Yeah, 5.6 is there. 5.6. Pressure, temperature, velocity, specific heats, neglect potential energy, pressure and temperature of surroundings, available energy of the airstream will be. See, pressure is there, temperature is there, and as well as velocity is there. So in case of a, what is there? It is a pipe, simple pipe is there. So that is P1 5 bar, T1 500 Kelvin, and V1 is 50 meter per second. Okay, fine. Yeah, so now what do you need to do? In that case, if the pressure and temperature of the surroundings are given to be as 1 bar and how much? 300 Kelvin. So what is happening in this? P naught is 1 bar and T naught is how much? 300 Kelvin, right? So now in this case, neglect the potential energy. Delta P is tending to 0 and del W will be 0, right? Del W will be 0. Now we need to calculate it with the help of what? We need to calculate it with the help of surroundings. So for surroundings we need to find it out. Please pay attention. For surroundings we need to find it out, which is very important. Let me just have some water. Okay. Yeah. So let's see. Let us see. Now available energy. What did I tell you? For a process, it is maximum useful work. For a process till dead state. Please remember, that is why this is given. That is why these are given. Arey Baba, these are given. Why? Because it will achieve at dead state. With respect to dead state only, you will be calculating available energy. See, available energy or availability for available energy for a process or availability, if you need to calculate, you have to do it for dead state only, right? So now you have available energy. How would you do that? That will be H1 minus H2 plus T naught S1 minus S2. Am I right? That will be T naught S1 minus S2. And since there is some kinetic energy as well, you will be asking, sir, why kinetic energy are you taking? Why are you so much interested in kinetic energy? Let me tell you. Let me tell you. When we derived this formula yesterday, or let us say 2, we derived it from SFE. You remember? And in that, we neglected kinetic energy, pressure energy, and potential energy. Potential energy is still neglected. It is still negligible, but kinetic energy changes are given. You can't neglect it now. You cannot neglect it now. Can you? Cp T1 minus T naught plus T naught. Of course, T naught is the new T2. T naught is the new T2. How much is it? It is given as 300, right? That is it. And minus T naught. Why am I writing plus? Who told me to write plus? Anyways, it will be minus T naught let me write the values down. See, with respect to surroundings, it will be 0 because eventually at dead state, velocity will become 0. Why? I'll tell you. Why? I'll tell you. The reason for that being, surroundings can be taken as a pipe of infinite dia. Therefore, area tends to infinity. If area tends to infinity, means velocity tends to 0. Am I right? If area tends to infinity, which means velocity tends to 0. Simple. Simple, is it simple? Yes or no? Yes or no? Now can you solve this? Of course you can. Everything is given. All you know, you can do this by using tedious equations. You can solve it. Okay? Okay? That is available energy. And please try and match the. I needed to tell you this concept. Why have I, let me repeat it once again. Why have I taken change in kinetic energy? Because the formula, standard formula which we got was by neglecting kinetic energy. But here, since kinetic energy is given, we cannot neglect. And since it is given, we cannot neglect, we have to take it. Then why V2 is taken as 0? The reason for V2 being 0 is, and hence eventually V2 squared by 2000 being 0 is, that it is going into the surroundings. Surroundings is very large dia pipe we can consider. Means area is tending to infinity, means velocity is tending to 0. Got it? Next question. Okay, you want to take the screenshot? Take the screenshot, please. Take the screenshot, please. Then we'll move forward. Okay, because next question is big, I guess. Yeah, next question. 5.7. A source at a temperature of 500 Kelvin provides 1000 kilojoule of heat. The temperature of surroundings is 27. Maximum useful work. Oh my god, can't you calculate it? See, there's a source, there's a sink. Okay. The temperature of this surroundings is 300 Kelvin. This is your 500 Kelvin. What is the maximum amount of work which you can obtain? You can obtain it by using a Carnot engine in this. Yes or no? Of course. Okay, so let's calculate the efficiency of Carnot engine. It will be 1 minus 300 over 500. That is how much? 1 minus 3 by 5, 2 by 5, 40%. Okay, 1000 kilojoule is supplied. Kilojoule. So maximum work will be W max will be Q into efficiency of Carnot. So 1000 equals to 400 kilojoule. Okay, simple. Simple. Maximum theoretical work obtainable when a system interacts to equilibrium with a reference environment is called exergy. We have already dealt with this exergy. What is exergy? Maximum obtainable work when the system reaches dead state. Isn't it? That's great. 5.9. A reversible heat engine receives 2 kilojoule of heat from a reservoir at 1000 Kelvin and a certain amount of heat from a reservoir at 800 Kelvin. It rejects 1 kilojoule of heat to a reservoir at 4 Kelvin. Net work output. This is a kind of a question which we have done already in chapter number 3. But nevertheless, let me tell you. 2 kilojoule, 5.9. 1000 Kelvin, 2 kilojoule, right? Certain amount of heat, some Q is receiving it, it is receiving at 800 Kelvin, Q, and it rejects how much? 1 kilojoule to 400 Kelvin. It is a reversible engine. Now, net work output, oh my god, can't you solve it? Cyclic integral del Q by T0 baba. Very simple yaar. Coming to how much? 1000. Coming Q at 800 minus 1 400. Can you solve it? Can you solve it? Right? Reversible. Now you can easily find out what is the value for Q, and W equals to, W is this obtained, 2 minus Q minus 1. Okay? Simple. Understood everybody? 5.10. Let's deal with 5.10. One side of a wall is maintained. Find the irreversibility. Surroundings temperature is this one. See, this is the question which was asked earlier in the exam and which we have done in the entropy. See, one wall is maintained at 400 Kelvin, the other is maintained at 300 Kelvin, right? Heat is being transferred at a rate of 1000 watt. This type of question has been asked already. Surroundings temperature is 298 Kelvin. So what is irreversibility? It is T naught delta S. And how to calculate delta S universe? I've already taken a question. Similar question has been done. So 298 will be 100 is leaving this wall. 1000, sorry. 400 minus plus going into this wall. 1000 over 300. So you will get the result. I will be calculated. Simple, yaar. Next question. Okay, please take the screenshot. Please take the screenshot, then we'll move forward. Please take the screenshot, then we'll move forward after that. Please take the screenshot, everybody. Please take it. Okay. Now, 5.11. Next question, 5.11. Water flowing at a rate of 1 kg per second. Oh my God, this you will do. This I am giving you as a homework. It's very simple. Simply delta S universe, system plus surroundings. Okay. So this is pretty much it. Availability is done. And it is simply, let me tell you, whatever questions we did, it was all about calculating the entropy change of the universe. That's all is important. Okay. See you guys in the next session. That is tomorrow, marathon. We are finishing it up. We're not starting thermodynamic relations as of now. Reason being that it'll take much of a time, and also I wasted quite a time in recording in without sound. Earlier I have recorded without sound everything now, so it was double the trouble. So pardon me for that. Tomorrow we'll start with our marathon at 2 p.m. Please be there. Thank you so very much. Jai Hind.